In the last lecture, I introduced state machines and explained how they are very useful and often allow us to write much less code to express the logic of a smart contract. And part of the reason is that there's a lot of sharing between on-chain and off-chain code due to the use of these constraints. And another reason is that a lot of boilerplate is encapsulated in the state machine machinery, like the handling of this NFT stake token. And in today's lecture, I want to give another example because the concept is really very important. So I want to show another example of using a state machine, and I want to talk about testing. So first I'll present the example, and then I'll explain various ways to test that code. The example I picked is a contract that allows somebody to sell tokens. So the idea is that if I own tokens, I can lock some of them in this contract, set a price, and then other people can buy it, and I get the money they paid for it. In the beginning, the seller, the person or party that wants to sell tokens, starts with an NFT. And it can be an arbitrary NFT, and it will just be used as before to identify the correct UTXO that contains the contract state. The first step is for the seller to lock his NFT at the script address of the smart contract we are about to write, and I call that TS here for token sale. So you create a transaction, submit a transaction that locks the NFT at this address, and as datum we will use a simple integer which indicates the price of the token, and this starts off as 0. There will be several operations that the seller can do. One of those is setting the price to a different value, and in order to do that, the seller needs to submit a transaction that has the current UTXO as input and the updated UTXO as output, where the datum has been changed to a different price. So in this example, the seller set the price to 6 ADA per token. Another thing the seller can do is actually lock some tokens in the contract. So in order to do that, he has to create yet another transaction that has as input again the contract, the UTXO locked at the contract, and a UTXO containing some tokens that the seller owns, and as output just the updated UTXO at the contract address, which now contains the provided tokens as well. So in this example, the seller provides 5 tokens to the contract. Now for somebody to buy tokens, there needs to be created a transaction by the buyer that as input, of course, again has this UTXO sitting at the TS script address and the buying price in ADA. So if somebody wants to buy 2 tokens, you would create a transaction that has as input the price 12 ADA and the UTXO at the TS script address. And then 2 outputs, one the updated contract state, where now the tokens are taken out and the price has been added, and one output going to the buyer with the tokens he just bought. Finally, there must be a way for the seller to retrieve tokens and ADA. So in this example, if the seller after the sale wants to retrieve all the ADA and 1 token, he would create a transaction that again has the script UTXO as input, and then 2 outputs, one with the updated script UTXO, when now some tokens and some ADA have been retrieved, and one to himself with the retrieved funds. And of course, this diagram just shows one example. So the idea is that these operations can happen in any order. So the price can be set several times, tokens can be added, tokens can be bought, and funds can be withdrawn in arbitrary order. I implemented this in this week's code, and I called the module token sale. And let's first look at this type, data token sale. So that's the parameter I will use for the contract. It has 3 fields: the seller, the seller's public key hash, then this token, that is the token being sold in this token sale, given by its asset class, and finally the NFT that is used to identify the correct UTXO. And as redeemer, I provide exactly the operations we saw in the diagram. So set price to a new value. This is the token price in Loveless. Add tokens, where the argument gives the amount of tokens to add. Buy tokens, where the argument gives the amount of tokens to buy. And finally withdraw. This is actually like bad practice to just give integer arguments because now it's not clear which is which. So in this case, the first one is supposed to be how many tokens to withdraw, and the second one, how many Loveless to withdraw. Then I have my helper function again. Loveless is that given a value extracts the amount of Lovelesses in there. I also used that in last week's code, I believe. And now the transition function of the state machine. So the first argument is the parameter. And then recall we get the state. And in this case for datum, we will use integer. As I mentioned before, the price of the token and the redeemer. And then we must return a maybe constraint state. So we return nothing if the corresponding transition is illegal, and just something if it's not. And then we must provide the constraints and the new state. And recall the state contains the datum and the value. So similar to last time, I split this given state into the value and the datum, and then I have the redeemer. So I pattern match on these triples in this case statement. And now I simply go through the 4 transitions. So the first one is for set price. And if I want to set price to a new price P, I only allow that if the new price is non-negative. And in that case, the constraint is that that must be signed by the token seller. So only the token seller can change the price. But that's the only constraint. And the new state, so now the new datum will be this new price P that comes from here. And I don't change the value in the contract. And this is now a bit unfortunate because I mentioned last week that the state machine library hides all the boilerplate that you need to handle this in NFT. But for some reason, I'm not really sure why, there's a discrepancy like on the left-hand side and on the right-hand side. So somehow on the left-hand side, this V does contain the NFT. But on the right-hand side, it's not supposed to contain the NFT. So therefore, even though what I want to say is that don't touch the value doesn't change, I have to subtract the NFT here on the right hand side because the library for whatever reason adds it again. So I think this is like not an ideal design, but it's what it is. So I always, also in the other cases, I always subtract this NFT on the right hand side because then the library will add it again. So the point is the NFT is supposed to stay in the contract forever. Okay, so for add tokens, I check that it's a positive amount. I could again check that only the seller adds tokens, but you must imagine that this contract is provided by the seller. And the seller doesn't care if somebody else adds tokens to his contract. That would just be a free gift. So people would be silly to do that because they would just lose the tokens. But the seller has no reason to forbid this. So therefore, I didn't add any constraints on this add tokens. So anybody can add tokens, although in practice, of course, only the seller has incentive to do so. So no constraints. I can use the memty that comes from the monoid class. In the new state, so I don't touch the price. The price doesn't change. And the value is just the old value. I again have to subtract this NFT. And now the amount of tokens that are specified here, the N, have to be added. Then the buy tokens case, again, the amount of tokens to be bought is positive. Again, I don't need any constraints on the transaction. Anybody can do buy tokens. Of course, the seller normally wouldn't, has no reason to, but that's fine if he insists. Okay, and again, I don't touch the price. This is the old value I have to correct for the NFT. Now I subtract the tokens that were there and I add the price. So this is just the number of tokens times the price per token in Loveless. And finally, withdraw. So I insist that it's non-negative values. Remember, the first argument is the amount of tokens to withdraw. The second argument, the L, is the amount of Loveless. This case, I again insist that the seller signs it, because otherwise anybody could take funds out of this contract. And the new state, I again don't touch the price. This is the old value corrected for the NFT. And I just subtract the tokens and I subtract the Loveless. And all other state transitions are illegal. Oh yeah, and as a helper function, I have NFT, so this is just the value of the NFT that I use here in all the cases to correct for that. So once again, the meaning is that the NFT just stays in the contract. It is there in the first place and it never leaves it again. In this case, I can construct my state machine easier than I did last week, because last week we had this one condition that couldn't be expressed in constraints, and I had to put this into another field of the state machine. But in the default case where you don't need that, where constraints are enough, like this case, there's a helper function, a smart constructor for state machines called makeStateMachine, and just takes 3 arguments. The first one is the state token as before. So we want to use our NFT, therefore I provide just that. The second is the transition function that we just defined. And the last one is indicating which states are final. And in this case, there is no final state. So the idea is once this token sale has been set up, it will always be there. And that's it. Then we have our state machine, and we can use the usual boilerplate to use it and turn it into a Plutus smart contract, into Plutus on-chain code. So we get the validator and the script instance and so on, and the address. Then we can easily construct a state machine client. So recall that is to interact with the state machine on the off-chain side using makeStateMachine client as before, using the provided instance. Then I just have 2 helper functions to deal with the external contracts I want to use. That's also similar to before. I want to, in order to mint this NFT, I want to again use the currency module, and that has its own error type. And I, as always, want to use text as error type. Therefore, I use the map error to convert this currency error into text. And I do the same for using contracts from the state machine library. So I convert this SM contract error into text as well. Now for the off-chain code, I just define this constant here, NFT name, as NFT for convenience. And then the first contract I provide is start token sale. So that's supposed to be invoked by the seller to set up this state machine. The first argument is a maybe currency symbol. So the idea is if you pass in nothing, then the contract, this off-chain contract, will mint a new NFT for you using the forge contract method from the currency use case. But you can also provide just currency symbol if the NFT already exists. And I mostly did that to make testing easier later. Then the asset class is the token you want to trade. And I'm using this writer monad type here, again with the last type. And the idea is that once the token sale has been set up, it gets written here so that other contracts have the possibility to discover that. But I also return the created token sale in the end. And how does it work? So I look up the public key hash of the seller, and then I check whether NFT currency symbol has already been provided or not. So if not, I use this forge contract as before to mint a fresh NFT. and otherwise I just use the one that was passed into the function. And then I can define my token sale. So I now know the seller, that's my own public key hash. I know the token that was provided as an argument, and now I also know the NFT. And I set up a state machine client and then use this run initialize that we discussed in the last lecture, using the client initial price of 0 and no funds in there. So the NFT will be automatically added. So no funds just means no additional funds on top of the NFT. I write this TS into the log, log a message, and I also return the TS. So that's the start function. Now I have functions for all the other operations, and they are extremely short. It's very simple now because this example is really ideal for the state machine approach. So I don't need any other code basically. And they are all very similar. So I just always use run step and invoke the correct transition from the state machine. So for example, for set price, I need the token sale argument to identify the correct contract and the new value of the price. And I just use run step with the client and then as redeemer set price to the provided argument P. And I just wrap that into this map error as M to convert it to text error messages, and I ignore the result. And I do exactly the same for the other three operations: add tokens, buy tokens, and withdraw. So this is really extremely short, the off-chain part of the contract. The only reason the start TS function is a little bit longer is because I also deal with these two cases, whether the NFT is already provided or whether I have to freshly mint it. Now I define three schemas. So one is for the seller who wants to start the contract. It just has one endpoint start, and it takes the currency symbol and the token name of the asset to be traded. So this is the case where the NFT will automatically be minted. And then more for testing purposes, I also provide a start schema prime, which additionally takes the currency symbol of the provided NFT. And then I have one schema for using the token sale contract once it has been started, which contains endpoints for the four operations: set price, add token, buy token, and withdraw. Then I implement these. So start endpoint simply called start TS prime and then recurses, and start TS prime calls endpoint to block until the parameters are provided, and then runs the function we defined above using nothing as the first argument, indicating that the NFT has to be minted. And I wrap it into handle error, and if there's an error, the handler simply logs that error. Start endpoint prime is very similar, except that now I get these three arguments. So instead of providing nothing for the first argument of start TS, I provide just CS1, where CS1 is the first component of this triple that the endpoint provides. Use endpoints, also no surprises here. So I give the choice between the four endpoints: set price, add tokens, buy tokens, and withdraw. And they just use the functions we defined earlier, but get their arguments fed in from an endpoint call, and everything is wrapped into an error handler so that even if there's an error, the contract won't crash and instead just log the error. In order to try it out, let's first use the emulator as we did before. So I define a run my trace function that again uses run emulator trace.io prime with a custom emulator configuration and my trace. We'll get to my trace in a minute. Let's first look at the custom emulator configuration, where again I specify an initial distribution that doesn't give only ADA to the wallets, but also some other token. So the idea is every wallet gets 1000 ADA, and in addition to that 1000 tokens, where token is just arbitrary currency symbol AA and token name capital A. This these underscores make it easier to read large numbers, and they are provided by a extension, GHT extension, that's called numeric underscores. So we'll only use 3 wallets, 1, 2, 3, and each of them will have 1000 ADA and 1000 of these tokens. Now for the trace, first we activate the start endpoint, not primed, so the one where the NFT is minted automatically for wallet 1, and call the start endpoint with currency and name that correspond to this token that the wallets all own in the beginning. And just to give this contract enough time to mint the NFT and create the initial UTXO of the token sale contract, I wait for 5 slots. That's too much. 2 should be enough actually. And then query the observable state. Remember, we wrote the last token sale using tell in the start contract. So this could be nothing or just. And if it's nothing, something went wrong. So we log an error message. And if it's just token sale, then we log the token sale that we got. And now we can activate use endpoints for wallets 1, 2, 3. And remember, this use endpoints contract is parameterized by the TS. That's why we needed that value. Then wallet 1 sets the price, calls the set price endpoint to 1 million Loveless. So 1 ADA will cost 1 token. Again, we wait for a generous amount of time. Then wallet 1 adds 100 tokens to the token sale contract. And we wait again. Then wallet 2 buys 20 tokens. So now 80 should be left in the contract. And 20 should have gone to wallet 2. But wallet 2 has to pay 20 ADA for that. So the contract should now contain 80 token and 20 ADA. We wait again. Now wallet 3 buys 5 token. That means that now in the contract there should be 75 left. And there should be 25 ADA in there. Finally, wallet 1 calls the withdraw endpoint, retrieves 40 of the 75 tokens, so 35 should be left. And it also withdraws 10 ADA, so 15 should be left in the contract. So let's try to run this trace in the REPL. So I go to the REPL and execute run my trace. And there we go. So the first endpoint call is to start. And we see this creates 3 transactions. 2 of those are from this Forge contract in the currency use case to create the NFT. And the third one is then to set up our initial UTXO for the token sale. And we log that the token sale has been created. Now we successfully read this token sale value from the observable state and start the 3 contract instances for the use contract. This is the set price. This is the add tokens call, and then the 2 buy endpoint calls by wallet 2 and 3, and finally the withdrawal by wallet 1. And if we check the final balances, all wallets initially owned 1000 tokens and 1000 ADA. Then wallet A added 100 tokens to the contract, so was left with 900, but then in the last step retrieved 40, so that's why it has 940. And it also retrieved 10 ADA, so we see that it almost has 1010 ADA now. The difference is due to transaction fees, of course. Wallet 2 bought 20 tokens, has now 1020, but paid 20 ADA for that. So now has almost 980 ADA. And wallet 3 bought 5 tokens and has 995 ADA minus transaction fees. Finally, the script still contains the NFT that will forever stay there, and 35 tokens that are left, and 15 ADA. Originally, at some point, there were 25 ADA in there, 20 from wallet 2 and 5 from wallet 3, but wallet A withdrew 10 of those, so 15 are left. So everything seems to work as expected. You can find Tasty on Hackage, and there's also an example. So basically, you have a main program that uses, for example, default main and then some tests. And tests are of type test tree. And as the name suggests, a test tree is a tree of tests. So you can group tests and have subgroups and sub-subgroups and so on. There's special support for tests in Plutus, and that is provided in module plutus.contract.test in the Plutus-contract package. And there are various types of tests that are supported, but today we'll only look at two of those. One that works with emulator traces and one that's much more sophisticated and uses so-called property-based testing, which we will look at next. But let's start with the emulator trace-based tests. So in this module, there's the chapter on checking predicates, and there we see the connection with Tasty. So there's this check predicate function. It takes a descriptive name of the test, then a trace predicate. We'll get to that in a minute. And then an emulator trace, like the one we just used to manually test our contract. And the result is a test tree, which we just saw is the type of tests that Tasty uses. So by using this check predicate, we can produce something that the Tasty framework can understand. There's also a variation, check predicate options, where we can set some options. So there's one additional argument of type check options. And if we look at that, then we don't see any constructors, so they are hidden. And in order to access the options and set various options, you need these operations here. And they have this weird type that we haven't seen yet, this lens prime. And that is related to something called optics in Haskell. And that is a huge topic by itself. And whole books have been written about optics in Haskell. So I will ignore this for now, just show you how to use this emulator trace, and then say a couple of words about optics. Unfortunately, I can't go into detail there. And I find it a bit unfortunate that you are basically forced to use these optics in order to work with this library. It would, in my opinion, have been better to expose the constructor so that we could have, without using optics, interacted with this check options type, for example. But in any case, so this we can use here, this emulator config lens, to actually set an emulator config like we did before when we ran the manual trace to specify an initial distribution of funds. So let's look at this trace predicate now. And that specifies some predicate, some condition, some check that the emulator trace should satisfy. And this is then what will be tested when you run this test. And first of all, we see that there are some logical combinators. So you have not to negate predicate, and you have logical AND to combine two predicates to the combination. So this combination will only be true if both of the arguments are true. And then we see there's a variety of possible trace predicates, various checks you can do, checking some UTXOs and check that the contract has completed or not completed and so on. But as an example, I will only use one that actually checks funds. So here we have wallet funds check, which given a wallet and a value determines that after the emulator trace has executed, the funds in the wallet have changed by this value. And interestingly, fees are ignored. So we would have a hard time to write precise tests if we had to take fees into account, because we don't know exactly how high they are, and then we would have to like do approximations and so on. So it's nice that we have this available where we can ignore fees. But there is also a variation on this valid funds exact change where fees are taken into account. And as you see, there are lots of other available trace predicates. So if we go back to the module where I defined my trace, you see there's one additional function in here that I haven't shown you before, and it's called tests, and it's of type test tree, and it uses exactly this check predicate options. And for the options, I want to use the same emulator configuration that I used before, that we also used for the manual trace here at this point. I showed you that earlier. So I want to do the same. But now, unfortunately, in order to set that, I have to use these optics. So let's ignore that for now. Just this syntax works. So these are the default check options, and then I modify the emulator config in it to have this value. Then the next argument is the name, so I just call it token sale trace. And now I use this AND combinator to chain together 3 different trace predicates, and each of these uses this wallet funds change, where I ignore the fees. And I just say, okay, wallet 1, after being run, should have 10 ADA more and 60 tokens less. Wallet 2 should have 20 ADA less and 20 token more, and wallet 3 should have 5 ADA less and 5 tokens more. We can try this out in the REPL. I just need to import test tasty, and then I have this default main available, and I can do default main tests, and it passes and says okay. Let's see what happens if it doesn't pass. So let me just change a value here. Let's say instead of 60 I have 50, and let's run it again. And now we see we get a failure, and it gives us a nice error message. It says what it expected. The funds should change by -50, but in actual fact they changed by -60. And we also get an emulator log that we didn't see before when the test passed. This is probably the simplest and easiest way to write automatic tests for Plutus contracts. You simply write one or more emulator traces and then use check predicate in combination with appropriate test predicates to check that those emulator traces lead to the desired result. And what you get is more or less traditional unit tests. Before I get to the second way of testing Plutus contracts that I want to present today, I want to give a very brief introduction into optics and lenses. And there are various competing optics libraries on Hackage, but the most prominent and also most infamous one, and the one that the Plutus team decided to use, is called Lens. And it's authored by Edward Kmet, who is probably the most prolific contributor to Haskell libraries. And you see already on the Hackage page, the overview page of the Lens library, there's this scaring diagram. And there's a whole zoo of optics. So there are lenses and prisms and traversals and ISOs and whatnot. And here's a nice diagram with all the operations, or some of the operations, that the Lens library provides. And what optics are all about is reaching deeply into like hierarchical data types and inspect parts that are deeply hidden in a data type and manipulate them. Let's look at a very simple example that I provide in module Lens that shows the problem and how optics address that problem. So let's look at a company data type. It's just a new type wrapper around a list of persons with a accessor called staff. And I provide an underscore in front of staff that has no semantic meaning. So it's just another letter in this case. But when dealing with lenses, it's just convention to call fields with a leading underscore. So we have this company type, wrapper around persons. Then person is a record type with 2 fields, name and address, where name is just a string and address is of type address, again following this convention to use underscores in front of names. And finally, address is yet another new type wrapper around a string, where access are called underscore city. So there's nothing advanced going on. That's basically first week Haskell. And just as an example, I define two people, two persons, Alejandro and Lars, with name and address. And finally, I define a company where the staff consists of these two persons. And now the task is to write a simple function, goTo, that gets a string as argument and a company, and is supposed to create a new company, which you get from the old company by changing all the city names, all the cities of all the persons in the staff of the company to the given string. So if I apply that to IOHK and as string argument I use Athens, then in the end I should get a company with, again, two persons, again name Alejandro and Lars, but now both of those should have city Athens. And I mean, that is not very difficult. So you can easily do that. You don't need any advanced Haskell for that, but it's a bit messy even in this simple example. So if I implement this, go to there, so that's the new city and company, then I can use the old company and update the staff field in it. And this is, remember, a list of persons. So I write a helper function move person, and I map this helper function over the list, over the staff of the given company. And now in order to implement this move person, I take the existing person and then use record update syntax to change the address. So the name will be the same as the name of P, but I change the address. And what do I change it to? Well, I take the existing address and change the city name to there. We can try this out in the REPL. So I can first look at the original company. And it's as expected. And now I can apply goTo Athens to IOHK. And we see that the deep inside, I mean, a couple of levels down in the company, now we have changed the city names here to Athens and here as well. So we see that dealing with nested record types, even though conceptually they are not complicated, is just, or can be quite messy, because you always have to like keep the old fields in place and update the new ones. And if it's nested, that can be quite messy. And this is exactly what Optics try to solve and make easier. The idea is to provide something like first-class field accessors. And in the end, it's almost as easy, or it's very similar to dealing with such data types in Haskell than it is in an imperative language with mutable data types using these dot accessors. So in C# or in Java, you could write something like company.staff.name or .address.city, for example. And with lenses, it looks very similar. So in that sense, when I introduced monads, I said that some people say that monads offer a programmable semicolon, because the semicolon is normally what's used in a lot of programming languages to chain statements together. And with a monad, you can customize how this chaining of statements works. And similarly, you can say that optics provide a programmable dot in the sense of an accessor dot, like in Python or Java. And in order to work with lenses, I mean, you can, if you want to, implement them by hand, but the lenses library provides some template Haskell magic to do that automatically, but that expects these underscore convention. And that's called make lenses, and then you provide the types for which you want these lenses. So I added these make lenses company, make lenses person, make lenses address. And the names of the lenses will be the names of the original fields without the underscore. So that's why there's this convention. The fields will have the underscore and the lenses won't. There's a way to inspect what code template Haskell writes at compile time from the REPL. For that, you can activate a flag called dedump splices. Now if I reload, nothing happens. I think I must change the code. So let me just do this. Okay, and there we go. So this is now what template Haskell does. So we see the make lenses for company gives us a staff ISO, so that's a type of optic, from company to list of person. Then make lenses person gives us an address lens from person to address, a name lens from person to string, and finally make lenses address gives us a city ISO from address to string. And ISO and lens are two different types of optics, but the convention or the order of type arguments is always the same. So you always have two type arguments, at least for these primed varieties. There are also more general optics with 4 type parameters, but these with 2, the first one is always like the big data type, and then the second parameter is the one you zoom into, the part. So it's called optics because you can have this mental image of zooming into a data type. So the staff lens or ISO provides a way to zoom in from a company to the staff, which is a list of persons. The address lens allows us, given a person, to zoom into the address field of the person. The name lens gives us a way to zoom in from a person to the name, which is a string. And finally, the city ISO allows us to zoom in from an address into the city name string. And we can try these out. So if we take, for example, Lars, and want to use the name lens, one way is to just look at the result of zooming in. So I can do Lars and then use one of these funny operators provided by the lens library. That's this caret dot. And then one of the lenses. So let's take the name lens. I see I have to import control lens for this to work. Then I indeed get Lars, which is not very exciting, but at least it works. Similar if instead I use the address lens, then I get the address. So one very important feature of lenses, and that makes them so powerful, is that you can compose them. So using the address lens, I get from a person to the address. But the address itself is again a record type, which has this city field. And I can chain lenses together if they are compatible. So I have something going from person to address, and I have something going from address to string, then I can combine them. And the combination is actually just the usual function composition dot, which is actually very cute because it's exactly like in a imperative programming languages with the accessor dot. And there's some quite advanced type level machinery going on behind the scenes to make that work, but it works. So I can just do address.city, for example, and now I zoom in 2 steps. So from the person, Lars, first to the address and then to the city, and I see the result, which is Regensburg. And you can't only view the result of zooming in, you can also manipulate. So you can set. So if I want to, for example, set my name to something else, I could do the following. So here the syntax would be this ampersand, which is basically just function application the other way around. So the argument comes first and then the function. And now a lens, so name, and now colon tilde and new value. So if I want to, for example, rename myself to all uppercase, I can do this. And now the result is a new person where the name has updated. And again, I can compose. So I can do, for example, name dot, no, not name address, and then dot city. So I can reach into the person to the address and then deeper inside to the city and update the city from, for example, Regensburg to Munich. And it also works. So name and address are lenses, and lenses are, I mean, the intuition is that it's a part of a data structure, like the field in a record type. There's a different type of optics called traversables, which doesn't only zoom into one field, one thing, one smaller part, but into many simultaneously. So if you have a list, it would zoom into each element. So for example, I can use a list of integers. 3, 4. And now I can use the each traversable, which works for lots of container types, including lists, and can set every element to 42. And now I get a list with 3 42s. And the cool thing is that various types of lenses can be combined, again, with the dot operator. So for example, I had this IOHK type, the company type. So I can have IOHK and I can view the staff that we have seen before. But now the staff is a list. So now, for example, I can compose that with the each traversable. So now I focus on each element of the list, which is a person. Now I can compose this with address and that with city, and finally set it to, for example, Athens. Oh, I wanted to set, not view. So what I have to do is this. And this is exactly what this goTo function achieved. So I reach into the staff, then reach into each person in the staff, into each person's address, into each address's city, and set it to Athens. So instead of this relatively messy code I wrote before using lenses, I can simply update the name of the city of each person in the company using this. If we go back to the code, that's exactly how you can implement this goTo function using lenses. So you just update the company using this composed lens, or not, it's not a lens then anymore because there's a traversable in there, this composed optic staff.each.address.city, and set it to there. And this is actually what I did here when I configured our test. So this default check options is of type check options, but there is a lens from check options to emulator config. And I just wanted to change the emulator config. So I can use this and then this emulator config lens and set it to the value I wanted to have. So that's how this works. And that concludes the brief excursion into optics. It's a fascinating topic. I love lenses and optics. I think they're really cool. You can do very cool things with that. But of course, it's not the topic of these lectures. The second approach to testing Bluetooth contracts I want to present today uses a concept called property-based testing. And that is quite a revolutionary approach to testing that is much more powerful than simple unit testing. And it originated from Haskell, and Haskell, due to its pureness and its immutable data structures, is particularly suited to this approach. But it has been copied by almost all other programming languages by now. So you get property-based testing libraries for Java and Python and C# and JavaScript and many more. And one of the inventors of QuickCheck, which is the most prominent and was the first library using this approach, is John Yu, who is also one of the original inventors of Haskell. And he and his company actually worked with IOHK to provide special support of this approach to testing Bluetooth contracts. But before we go to that, let's first look at vanilla QuickCheck for pure Haskell programs. In particular, property-based testing subsumes unit tests. So unit tests are just a special case. So we can have a very silly, simple unit test, something like simple prop, just of type Boolean, something like 2 plus 2 equals 4. Let's say ints. And if I import QuickCheck, then I can test this property with the QuickCheck function. And QuickCheck tells me it's okay, so the property is true. If I modify it and make it false, then it fails. Of course, that is not very exciting. Oh, by the way, I see the convention is to call these QuickCheck properties prop underscore, not the way I did it. Let's change that. Let's also make it correct again. Now to see a more interesting example, here's a implementation of a sort function, sorting list of integers, which is using insertion sort, which of course is not very efficient. So the idea of insertion sort is you sort the tail of the list and then insert the head of the list at the right position. And this is a buggy implementation. And in order to test it, for example, a property that we could test would be after applying sort to a list of integers, the resulting list is sorted. So I define a helper function isSorted that checks whether a given list of ints is sorted. So the empty list is sorted, a one element list is sorted, and a list with at least two elements is sorted if the first element is less than or equal the second element, if recursively the tail of the list is sorted. And using that, we can now provide a quick check property like this, that is not just simply of type Boolean, but instead is a function from list of ints to bool. So you can read that like a specification or like a mathematical property. Basically, it says for all list of integers xs, if you apply sort to it, then the result should be sorted. And QuickCheck can deal with such properties. So I can try that in the REPL and apply QuickCheck to this new property, sort sorts. And it fails, and it gives me a counter example. So it says for this list XS, this property doesn't hold. So if I sort it, the result is not sorted. So I can try that out. And indeed, I get 0 minus 1, which is indeed not a sorted list. And in addition to that, it also seems to have lost an element somewhere on the way. So how does QuickCheck do that? So if you provide a function with one or also more arguments to the QuickCheck function, it will generate random arguments for the function. So in our case, because we have one argument of type list of ints, QuickCheck will generate random list of ints, and then for each of these random lists, check whether the property holds. And if it does, then the test passes. But if it doesn't, it will report the counter example. However, we see that here in this error report, it says after 8 tests and 4 shrinks. So this means QuickCheck tried 8 random integer lists and then found a counterexample where this property didn't hold. But then it didn't simply report the list it had at that point, but it tried to simplify it, and this is called shrinking. And that's also a very powerful feature of QuickCheck, because often the counterexamples, the random counterexamples that QuickCheck finds are very complicated, very long lists with very long numbers. But then once a counterexample has been found, QuickCheck tries to simplify these counterexamples. So in the case of list of ints, it might try to drop an element of the list that it found as a counterexample and check whether the property is still violated, or maybe make some of the numbers in the list smaller, until it doesn't find a way to get an even simpler example. And this is really very powerful and very useful, because if you want to debug, it's very important to have not only a counterexample, but a simple counterexample, as simple as possible. So it's this combination of random test generation and shrinking that makes QuickCheck so tremendously useful. And actually we can see what types of random lists QuickCheck generates. There's a function called sample, and this looks a bit weird, but bear with me. So the way QuickCheck does this random generation is via a type class, and the type class is called arbitrary with capital A. So we can actually ask for information on the arbitrary class. And we see there are lots of instances already. And we see it has 2 methods. One is called arbitrary, one is shrink. So arbitrary is of type gen A, and gen is yet another monad. And basically what it allows is it allows random number generation for values of type A. So it has various methods provided by the monad that allow you to do random generation. And the second method is shrink. So given an A, provide a list of simpler versions of A, whatever that means. That depends on the type, of course. And as I said, we have lots of predefined instances for this arbitrary class already. So in particular, we have one for int somewhere. And given an arbitrary instance for A, we also have an arbitrary instance for list of A's. And therefore, QuickCheck knows how to generate random ints. And now if we look at the result of the sample function, that just in I/O provides some of the random int lists that QuickCheck would use. And there we see something interesting, that the further we go down in the list, the more complicated the list becomes. So the first random one is just the empty list, and then we get 2 with just one element with quite small numbers, -2 and 0. And then we get longer lists, but the elements here are still only one digit, and we get simple ones again, but towards the end we have like long lists with quite large numbers. So in addition to just providing random generation in this gen monad, there's also a concept of basically complexity. So not only if you implement that actually by hand, then you're not only supposed to somehow generate a random A, but also a random A of some sort of complexity. So a simple random A or a more complex random A. And then when QuickCheck actually checks a property, it starts with simple random arguments and then makes them more and more complex over time. And by default, it tries 100 different random arguments to a given property, but that can be configured. So I think 100 is a good default for development, but probably for production, especially for complex properties, something like 1,000 or even 10,000 is maybe more appropriate. So that can be configured. Okay, and so we see that this random generation for int lists work, and in our example we found this counterexample 00 -1. And if we inspect the code, it's quite obvious that there's one bug here, because all we do for a non-empty list is insert the first element into the tail, but we don't recursively sort the tail. So we can try to fix this and test again. And now it doesn't find a counterexample anymore. So this property now seems to be satisfied, at least for the 100 or 200 test cases we tried. However, if I try the original counterexample that we found before fixing this bug, we see that we still, we get a sorted list now, but it's of course still not correct. And this leads to an important point, that obviously QuickCheck can't do magic, so the results are only as good as the properties you provide. And what we see here is that this one property we have, prop sort sorts, is not strong enough to detect whether the function is actually correct. So in this case, we do get a sorted list, but it's still the wrong result. So for example, we could add a second property, prop sort preserve length, which states that after sorting, the result should be as long as the original list. So what we could say is, for example, length sort access equals length access. If we try this, then we do find another counterexample, 0, 0. And if we check sort of 0, 0, we see we only get the one element list. And the bug is here, because if x is less than or equal y, we append x to ys, but we forget about the y. So let's insert that there and try QuickCheck again. And it works. But of course, that is still no proof that our function is correct, because these two properties together, that actually the result is sorted and it has the same length as the original list is still not enough to fully specify a sorting function. For example, the sorting function could simply return a list of the same length where all the elements are 0. So that would be sorted and it would have the same length, but obviously it wouldn't sort the original list. So it's quite an art to find properties that are strong enough to basically guarantee that if they are all satisfied, there is no bug. But nevertheless, this quick check approach is much more powerful than traditional unit testing because it tests so many hundreds or thousands of random test cases and often finds examples that a human programmer that writes unit tests wouldn't have thought of. And with a few lines of code now, these two properties that I provided, I test hundreds of thousands of scenarios, which is much better than just writing 2 unit tests for specific lists. Now that we have gotten a brief overview of QuickCheck, we will apply it to testing of Plutus contracts. But there we encounter a problem, namely how do you use QuickCheck to test side affecting code that has effects in the real world, like on a blockchain. And that problem doesn't only arise with blockchains, it arises with all systems that use I/O, that have effects. And John Yu himself always uses the example of, for example, a file system. How would you test file system operations, like open a file, write to a file, close a file, read a file, and so on, using QuickCheck? And the approach one can use there is very similar to the one that is used for Plutus. And the idea is that you start with a model. A model is basically an idealized model of how the real-world system should work. So there must be some sort of relation between the model and the real system. So if the real system is a file system, then you could, in the model, have an idealized version of how you think files should work. And then what QuickCheck does in its random generation, it generates a random sequence of actions that you can perform on the system. So in the example of a file system, it would randomly generate a sequence of opening files, closing files, writing to files, reading files, and so on. And now you can basically step this model and the system in parallel. So you have some sort of action that you perform in the real world, and you apply the same type of action to your model. And then after that, your real system has progressed into a new state, and your model has also been updated. And then after this step, you can compare the two and check whether they are still in sync. And you continue this for several steps. So when our first QuickCheck example, we generated random list of ints, the idea for testing a real-world system is to generate random lists of actions and then apply those actions both to a model and to the real system and compare that the results are as expected and that the model and the real system stay in sync. And shrinking in this case would be if you have a list of actions that shows that there's a bug in your system, then you can, for example, drop some of the actions and see whether the problem still arises and try making this action list shorter until you can't drop any more actions from the list and still reproduce the bug. And this is exactly how the QuickCheck support for Plutus also works. So in order to test the Plutus contract, we have to come up with a model and define our expectations, how the various endpoints, for example, would change the model, and provide a link between the model and the real system. Or actually, it's not the real blockchain, it's the emulator, but in a sense that is like a real system. And then apply this QuickCheck machinery. So that's what we will look at next for the example of our token sale contract. So the code for this is in module spec.model, And here we import Plutus contract test that we saw before that provides basic support for testing Plutus. And now to use this quick check approach, we also import Plutus contract test contract model, which has all the machinery to define a model and link it to the real contract. Furthermore, we have test.tasty and test.tasty quick check. Test.tasty.quickcheck provides a link between QuickCheck and Tasty so that you can use QuickCheck properties in Tasty test suites. So to define the model, first define a data type TS state for token sale state. So that's supposed to represent the state of one token sale instance. And it has three fields: the current price, the current supply of Loveless in the UTXO in the contract, and the current supply of tokens in the contract. And now I define my model. That is now the model I was talking about in the diagram earlier. And that is just a map from wallet to token sale state. So the idea in this test is that I have several wallets, actually only two, and all the wallets run their own token sale. So we will have two wallets, and each of the wallets will run a token sale contract, and we will have two tokens, and the two wallets will trade different tokens. And the idea to use a map is that in the beginning, before the contract has started, there won't be an entry for that wallet, and once the contract has started, there will be an entry for that wallet with the current state. And I also implement lenses for that, because we also need optics in order to interact with the library, with this Plutus contract test contract model library. And now all the logic is in the instance of the type class contract model for this type. So here we provide how our model should behave and how it is linked to the actual contract. So first we have a so-called associated data type. So that's quite an advanced Haskell feature. So in type classes, you can have, instead of just methods that we usually have, also have data types. We have actually seen that before when we define validators and we define this dummy type that provides a link between the datum type and the redeemer type. So there we also use these associated types. So we need an associated action type, which represents the actions that QuickCheck will generate. And in principle, I just have one constructor in this action type for each of the endpoints we saw earlier. I just have additional arguments because now there are different wallets at play, and I must keep track which of the wallets performs an action. So start wallet means that this wallet starts a token sale contract. Then set price wallet integer means that this wallet, the second one, sets the price for the token sale operated by the first one, and it sets the price to this integer. Of course, we know from the contract logic that this should only work if these two wallets are the same, because only the owner of the token sale can actually set the price. But to make it more interesting, I want to provide actions also if somebody else tries to, and then we can see whether this is actually not working, because we expect that nobody else can set the price of token sale owned by a different wallet. Same for add tokens. So again, add tokens. This wallet wants to add tokens to that wallet's token sale and this many tokens. Then withdraw. This wallet wants to withdraw so many tokens and so many ADA from the token sale run by this wallet. That should again fail if the two wallets are not the same. And finally, buy tokens. So this wallet wants to buy from that wallet's token sale this amount of tokens. Okay, so this is the first ingredient, that we need this type of actions. The second ingredient is another associated data type. It's called contract instance key. So the idea is for each instance of a contract that we are running, we want a key that identifies this instance. And this is actually a so-called general algebraic data type. So it's a little bit different format to usual data declarations in Haskell that look like this. So the idea is that instead of just providing the constructors, you write them in this form, basically with their type signature. So this means we have a constructor start key that takes a wallet as an argument and then produces something of this type. And the reason we need these GADTs here, or the point of GADTs, generalized algebraic data types, is that with normal data types, the type parameters are always the same for all constructors. So if we have a parameterized type like list, for example, list of A's, then all the constructors that we have will produce a list of the same type A. And generalized algebraic data types allow us to have different type parameters. And we need this in this case because our contracts potentially can have different type parameters. So in this case, there are two types of instances. Recall we had the start contract and the use contract, and they had different type signatures. And so I provide one sort of key that I call start key for the first type, for the start contract, and it just basically as an argument has the wallet that does the starting. And here we see, so the type parameters are, the first one is the model we are just defining, and then the ones that come from the contract itself. So the state type, which is last token cell, if you recall in this case, then the schema, and here I use the primed version because I don't want to generate an NFT using this forge contract. I want to pass it in. That makes it easier to write the test if I know in advance what NFT I will be using. And text is the error type. And then there's the second type of contracts, the use type. And so I provide the instance key for that as well, that I call use key. And that takes two wallets as parameters. This is the one that owns the token cell we are interacting with, and that is the one that actually runs the contract. So similar to how it worked here. So same order of wallets. And this has different type parameters. Again, TS model, but there is no state. We don't use tel. And the schema is different. The error type is the same. Next, we need to somehow provide this instance tag function, which given such a key that we just defined and a wallet, a so-called instance tag or contract instance tag. And because we already know the wallet that runs the instance, because that was one of the arguments to our contract instance keys, we can ignore this wallet argument. And this instance tag type or contract instance tag type doesn't have an accessible constructor, but it implements the isString class. And we haven't seen that class before explicitly, but we have used it all the time when we use this GHC extension for overloaded strings. So when we can use string literals to, for example, define a byte string or a token name or currency symbol, all those types implement isString and they allow using string literals. And the way that is actually implemented is via a type class called isString, and that in particular has a method from string. So given a string, it converts a string into that type. And this constant instance tag type implements isString. Therefore, if we provide a string, we can construct something of that type. So the idea here is to simply use our key that we have here and show it because it implements show, and then write instance tag for some arbitrary text in front of that. I mean, that wouldn't be necessary. I just copied that from some code from the libraries where they do it like that as well. So it is just important that this instance tag function results in a different tag for each instance that we will ever run in our simulation or in our tests. And this is guaranteed here because the way these are set up. So we will have one start instance for each wallet and then one use instance for each pair of wallets. But of course, they are all different values of this contract instance key TS model type. And then when we show them, they will still all be different. And that's the important part here. Actually, there's a default implementation for the instance tag method of the contract model class. So you normally don't have to implement that yourself, but that default only works, at least right now, if you only have at most one contract instance per wallet. But this is not the case in our case because we will have actually three per wallet. One start instance and two use instances using the own token sale and the other wallet's token sale. So we have three contracts running per wallet, and therefore we are forced to implement that ourselves, this instance tag function. So the next one, arbitrary action, as the name suggests, is supposed to generate an arbitrary action. So action we defined here, and we must now tell the system how to generate a random action. And as argument, it gets the model state. We come to that later, but I don't need that here, and I can ignore it. One-off is one of the combinators provided by QuickCheck, and given a list of arbitrary actions, it randomly picks one of those. So the idea is I basically just provide a list to create random actions of these types using these constructors and then pick randomly one of those. And this is using something that we also haven't seen before. It's so-called applicative style. So recall when we introduced monads, I mentioned that monad as a superclass has applicative, but we haven't used applicative yet. And applicative is often very useful to write monadic code more compact. So basically, what this says is first run the monadic gen wallet action, which I should show first. This is here. So what this is supposed to do, it's in this QuickCheck gen monad, this random generation monad, generate a random wallet. And how do I do that? I use yet another combinator provided by QuickCheck, elements, that simply takes a list of values of the type I want to generate and then picks a random of those elements. So wallets is another helper I defined somewhere here. So wallets is just wallet 1, wallet 2, so it's just this 2-element list. So gen wallet will just randomly either pick wallet 1 or wallet 2. Okay, so what this means is we first use this gen wallet to generate a random wallet and then return the action start that wallet that we just picked. And this is just a more compact way to write it. This, of course, this operator we have seen before, this fmap, which comes from the functor class. So gen wallet is of type gen, capital Gen wallet, and start, as we see here, start takes a wallet and returns an action. So if we fmap that, we get something of type gen wallet to gen action. So the result is something of type gen action as we want. So it's a random action. And here for set price, we must pick 3 random arguments. So set price takes 2 wallets and an integer. So we use gen wallet twice to pick 2 random wallets for these 2 wallet arguments. And then gen non-neg, which is also defined here as a helper function, which randomly generates an integer, but a non-negative one. And actually there is something in the QuickCheck libraries to support this. There's a non-negative type that implements an arbitrary instance. And it's just a new type wrapper around integer, and with get non-negative I can extract the integer. So this arbitrary comes from the non-negative type that would generate something of type non-negative, but that just wraps an integer and I extract that integer with this get non-negative. Anyway, so this generates a non-negative random integer. Okay, and this is now where this applicative style really shines. So if I wrote that in a do block, for example, I would first call gen wallet and bind the result against something, whatever, w1. Then I would call gen wallet again and bind the result against something like w2. Then I would call gen non-neg, bind the result against P. And then finally I would return set price W1, W2, P. And using this operator, which comes from the applicative class, we can write this nicely and compactly like this. So conceptually, applicative is weaker than monad, and you can always use this applicative style if what you are doing, the actions in the monad you are invoking, don't depend on the result of previous actions. So in a do block, I can have some monadic action and then inspect the result, and depending on what the result is, do the one thing or the other. And that is not possible in applicative. But often monadic code doesn't make use of that power, and then we have this more compact way of writing it. But it's really just identical to using a do block. It's just more compact. Anyway, and I follow this same schema for the other constructors. So again, this one-off will randomly pick one of these lines, and then so decide on one constructor for an action to pick. So it will randomly pick a start action, a set price action, an add tokens action, buy tokens action, or withdraw action. And then once it has picked one, it will generate the random arguments for that constructor. Depending on what constructor it is, might be different types or number of arguments. So withdraw takes 2 random wallets and then 2 integers, non-negative integers, for how many tokens I want to withdraw and how many Loveless I want to withdraw. I can try this out in the REPL. So using sample that we saw before, and then I sample this arbitrary action that I just defined. I don't have this model state, but I know I'm not looking at it, so I can just use undefined. And let's see. And I get a couple of randomly generated actions. And we see that it indeed picks different constructors, and then for those constructors picks random arguments. For example, here's withdraw, wallet 1, 3, 5. And here we have another withdraw, wallet 1, wallet 2, 1, 2, and so on. Next is initial state. As the name suggests, it's the initial state of our model. Recall the model was this map from wallets to token sale states, and in the beginning there won't be any token sale yet, so it's just the empty map. So the initial state is the model that has the empty map, which means no token sale has started yet. Now comes the most complex function that we must implement to set this up, and that's called next state. And if you recall the diagram, I said you must know what effect performing an action has on the model, and that's exactly what this next state function does. If we look at the type of next state, we see it takes an action and returns something in yet another monad. It's called the spec monad. And that basically allows us, that monad allows us to inspect our current state, so the current state of our model, and also to transfer funds in our model. So this is not real funds on the real blockchain or in the emulator, but the model, among other things, also knows how many funds each wallet currently holds, and we can shift that. So let's look at an example. The start W. So this should now tell us what is the effect on our model if we encounter the start W action. So if wallet W starts a token sale. So here we see a function from the spec monad, withdraw. So the spec monad, the way funds are handled are very simple. So the wallets can have funds, and then there are contracts. They are like a black box that take funds. So withdraw means some funds go from a wallet to a contract. Doesn't matter which contract. So this line says the effect of start will be that wallet W loses the NFT. This NFTs, that's also again something that I've defined down here. So this is just lots of like helper definitions. So we already saw the wallet Then I just define currency symbols. So recall I said I want 2 tokens. So I need 2 tokens that are traded, and I need 2 NFTs for both wallets. So I just define them some arbitrary way. So the tokens that are traded will use currency symbols AA and BB, and the NFTs will be 01 and 02. Then token names I need for the traded tokens, so I use capital A and B, and then I just define each wallet's token that it trades. So wallet 1 trades the AAA token, and wallet B trades the BBB token. And I define the NFTs for the wallet. So wallet 1 will have the 01 NFT and wallet 2 the 02 NFT. And this is again the NFTs, but now not the asset class, but the actual value. So the value of that NFT. And finally, the token sales. So, and that is also the reason why I use this primed version of start, because I want to know which NFT is used so that I can compute this token sale value up front. Don't have to rely on the result of this forge contract. So this is the token sales that the 2 wallets will run. So the seller will be the wallet W, the token will be the token that I defined earlier, and the NFT will be the NFT belonging to that wallet. So, right. So this line means the effect on my model of the start W action will be, first of all, that W loses the NFT. It loses it to the contract. Remember, when we start the token sale, the NFT belong to this W, to the wallet that starts the token sale, is locked in the contract. Now, secondly, there will be an effect on the model state. Remember that this model state is a map from wallets to TS state, where TS state is this triple of price, tokens, and ADA. So what this line is supposed to say is that after I have started, there will be an entry in the map because the token sale has started, and it will have price 0, no tokens, no ADA. And this is on the left hand side here, this is another optic. So I use TS model, which here the TS model type had this TS model field accessor to get to the map with an underscore, and then this make lenses creates a lens for that. So I get from TS model to this map with the TS model lens, or actually it's an ISO, but that doesn't matter. Okay, so TS model gets me from the model to the map, and then this add comes from the lens library. That's a lens that works well with maps. So it's a lens from a map to the entry at a key. So at key W. And the type is actually a maybe because the key can or cannot be there. So this combined lens goes from the model to the entry at wallet W, which should be nothing at this point because if I haven't started the token sale yet. Okay, and this double dollar equal comes from the spec monad, and it takes a lens on the left hand side and then a new value on the right hand side. So this line says, okay, if the start action is performed, so this NFT is lost and the model changes, so the entry in this map at key W changes to this value. So that says that now in our model we have an entry for wallet W, and it has this state: 0 price, 0 tokens, 0 Loveless. And finally, this weight also comes from the spec monad. So the spec monad also has a concept of time. So I say the start will take 1 slot. Okay, and now basically I have to do the same thing for all the operations. So next one is set price. So what should be the effect of set price? So first I check whether the wallet that invokes set price is actually the same one that runs the token sale. And only if it is, I do something. Recall that only the wallet that owns the token sale can set the price. So if that's the case, funds don't move, so I don't need anything like withdraw again, but I must update the model. So this is so I use the same operator here, this $equal, but now a different lens. So instead of at, I now use IX, which is actually not a lens, it's a traversal. So it's similar to at, but the at results in a maybe, so I can handle missing keys. This IX does not. So TS model gives me the map, then this IXV goes to the entry provided by V, so the token sale run by V, but V is equal W, so I could also have written W here. So this now gives me the entry, this TS state of that token sale, and then I have the TSS price lens that goes to the price field, so this one here, the first component of the triple, and I set that to P. Actually, because IX is a traversal, it could be that the key is not there, so the token sale hasn't even started yet, but then the IX simply won't focus on it and nothing will happen. So that means only if the token sale has started do I set the price. If the token sale hasn't started, the IX simply won't have a target to focus on, and this line will have no effect, so the model won't change. So this basically says, okay, if set price is invoked, then reach into the model to the right entry in the map to the price component and set it to the provided value P. And in any case, wait one slot, whether it succeeded, whether W equals V or not. Okay, now add tokens. First, I check whether token sale for wallet V has actually started, and that's yet another helper function that I defined somewhere. Okay, so this is this. So given a model state, and the model state is this TS model type that we define, but it also has additional information. So for example, current funds and current time and so on. So given a model state and a wallet, I want to extract this TS state, so the state of the token sale of that wallet. And maybe that hasn't started yet, therefore maybe. And how I do that is using yet again optics. So this S, this model state, there is a lens provided that gives me the contract state. So the contract state is just this TS model type. So going from the model state to the contract state, then going to the map, and then using this add lens that I mentioned before. So the combination of these three optics zooms into this TS state entry. And if it's not there, it would be nothing. If it's there, it's maybe. So I look up. We saw this view operator from the optics library, from the lens library before. So this just reaches into the model state, to the contract state, to the map, to the key V, and returns me this TS state if it's there. Okay, then using that, I can write a slight variety of this function that doesn't have this first argument and just a wallet, but then returns the maybe TS state in the spec monad. And in order to do that, I use a feature of the spec monad. It has a function called getModelState, which, as the name suggests, gives me the model state. So in the spec monad, I can look up the current state of the model. I call it S, and then I apply the function that I defined just now to get this TS state, or the maybe TS state. And finally, yet another variation of this get TS state that I call has started. So given a wallet in the spec monad, it's supposed to tell me whether the token sale for this wallet has started or not. So I just use this get TS state that I just defined, and I know if I find it, if it's just something, then the token sale has started, and if it's nothing, then it hasn't. And there's a standard function in data.maybe in the Haskell prelude that tells me, given a maybe, whether it's nothing or not. And it's true if it's a just, and it's false if it's nothing. And I have to fmap because this is in the spec monad, so I lift this is just into the spec monad. So has started wallet tells me whether the token sale has started. So I'm using that here. So started is now true if the token sale has started. And if it hasn't, then I don't do anything, because then add tokens shouldn't have any effect. But if it has started, I also check that the amount of tokens to be added is positive. And if those two conditions are fulfilled, I continue. So there is another function in this back monad called ask model state. That's similar to get model state, but it doesn't take the complete model state. It doesn't return the complete model state, but instead takes a function from the model state to something, and then it doesn't give me the model state, but applies this function to the model state. View comes from the lens library and is just another name for this caret dot operator to view the result of zooming into a lens. And finally, there's a balance change W lens that is a lens from a model state to the balance change of that wallet. Balance change means how much have the funds of that wallet changed since the beginning of the simulation. So view balance change W is a function from model state to value. And then finally ask model state, this thing asks for the balance change of wallet W since the beginning of the simulation. So the reason I'm doing this is I want to check that actually the wallet that's invoking this add tokens has enough funds. So it wants to provide n tokens to the contract, but that of course can only work if it actually owns at least n tokens. So this is now the balance check, and so I look up the token, and now I must check whether it has enough. And token amount is the original supply. So I check that the token amount, the original supply of tokens, plus how many tokens it has changed since the beginning of the simulation. So this will now be the amount of tokens presently in the wallet, and that must be greater or equal the amount that the wallet actually wants to provide to the contract. Right, and if this is also satisfied, then I can again call this withdraw. So that says, okay, if all this works, then add tokens will succeed and the wallet will lose n tokens to the contract. And the state of the contract of the model will also change, because these n tokens will now be in the contract. So again, I reach to the map, to the right token sale that sits at this wallet that actually operates the token sale, and then to the TSS token field, which is the second argument of the triple here, and increase it by n. So before we had this $equal sign to set to a value. So we had this here, for example. And there's a different operator, $tilde, which doesn't set to a value, but applies a function to a value. So this says, however many tokens are there right now, add n to it. And in any case, I wait one slot. Okay, the next is buy tokens. So wallet W wants to buy n tokens from there's a token sale run by wallet V. First, check that n is actually positive. If it is, I use my helper function that I showed you just now to get the state of that token sale. That can or cannot be a nothing. So nothing would mean it hasn't started yet. So in that case, I don't do anything. But if it has started, so T is now this token sale state, I can use view with the TSS token lens to check how many tokens are currently in the contract. And that should be more than the amount of tokens I want to buy, or at least as many. So if not, I again don't do anything. But if so, then I look up the current price. I calculate the price I have to pay. And then the effect should be that my wallet W loses that amount of Loveless, but gains the tokens I buy. So deposit is the opposite of withdraw. It means that the given wallet gets a value from some contract. And finally, I update the model state. So I add the paid price and I subtract the bought tokens. And in any case, I wait one slot. Finally, withdraw. So this is only possible if the wallet that does the withdrawal is actually the wallet running the token sale. I again look up the state, and if it exists, so if there's a token sale going on, I check that I don't want to withdraw more than actually is there. So both for the tokens I want to withdraw and the Loveless I want to withdraw. And if this is satisfied, then I use deposit again to add that amount of Loveless and that amount of tokens to the wallet. And I update the model accordingly, so the Loveless are gone and the tokens are gone. And that completes the next state function. So this is, as I said, the most complex one to set up this model, to describe the effect the actions should have on the model. So right now the model is just some conceptual model that has nothing to do with the actual contracts we wrote earlier. I mean, the names, of course, are suggestive. I gave the names the same names as were used in the Redeemer, but there is no link whatsoever until now between this model here and the actual contracts and the actual endpoints we wrote. And this link is provided by yet another method in this class that we have to implement, and that's the perform function. If we check the type of perform in the REPL, we see it takes something called handle fun state. I'll explain that in a moment. Then it takes the model state and it takes the action we are performing. And I don't need the model state in this example. The handle will give me access to the actual contract handles. So let's look at an example. So we make a pattern match on the, or case distinction on the command. So if it's start W, so that means the action is starting the start contract for wallet W. And now this is now the link. So this is now actual emulator code. So how would this action manifest itself in the emulator? So in order to do this, I must call the start endpoint on W, and recall the argument I need here is this instance. So in the emulator, I start a contract instance and I get a handle, and now I must provide this handle. And this is exactly what the first argument is for. So this H argument, given a key, these are the keys, these contract instance keys we defined earlier. So given a key, it will give me the handle that I need to give to call endpoint in order to actually reach the right contract instance. And in this case, the key is start key W. That's exactly what we defined this key for the start contract on the W wallet. So giving that to the H we get a handle that we can provide to the call endpoint function. And now we must provide the arguments, and this is now, recall, it's the primed version where I want to hand in the NFT, but I explained earlier that I have them all computed. So this is the currency symbol of the NFT. This is the token what W is supposed to trade and the token name. And additionally, I do a delay of one slot afterwards. And this delay is just, it's nothing new, just a helper function here, which uses our well-known wait and slots that we have used all the time already. So just a shorter word of that. Okay, and all the others are in principle very similar. So for example, set price calls the set price endpoint, but now the key is not a start key, it's a use key. And because we want to set price, wallet W wants to set a price on the token sale provided by V. This is exactly why we use key VW here. And the argument is P. And the others are exactly the same, other endpoints. Finally, and this is now the last method I must provide, to implement all of this is precondition. So I have the option to say that certain actions are not supposed to be randomly generated at a certain point. So I can define preconditions under which it is acceptable to provide this action. And the preconditions I define here is that I say, okay, start. The precondition for start is that the model that this token sale hasn't yet started. So the S, the first argument of precondition, is again this model state. So precondition model state action is a condition that I can put that says, okay, in this state is this action possible. So this says start is only possible if I haven't yet started the token sale for wallet W. And for the others, I do the opposite. So I say this is only possible if it has already started. Okay, and this now finally completes the definition of this contract model class for our TS model. And now there's just, I need eq and show instances for my contract instance key type, and I want to derive them, but because it's a GADT, sometimes deriving doesn't work as nicely as it does with other Haskell data types. But there's something called standalone deriving. So instead of writing this deriving eq or deriving show directly behind the data type definition, I can have this standalone lines, and the syntax is like this: deriving instance eq and deriving instance show. And that needs actually a GHT extension, standalone deriving. Okay, and I think that is it. So now not quite. So this sets up everything. One more thing we need, we must provide the instance specs we actually want to run. So we defined these keys, but now we must somehow link them to actual contracts. That we haven't done yet. And this happens here. So this is a list of contract instances we want to run. And such a contract instance spec type takes 3 arguments. The first is the key, the second is the wallet, and the third is the actual contract that is supposed to be invoked with that. So we have 2 cases. We have the start keys and the use keys. So for the start key W, so that's the key, the wallet is W, and the associated contract is the start endpoint prime. And we do this for both wallets. And the use keys, so the key is use key VW, the wallet it runs on is W, and the contract is use endpoints. And recall, use endpoints takes a parameter, namely the token sale. So we look up the token sale belonging to wallet V. And we do this for all pairs of wallets. So there will be 4 of these instances and 2 of those. And this we have seen, this we have seen. And now finally we can define a quick check property. So this is now the link between all of this work, between this model and quick check. And there's a function in plutus.contract.test prop run action with options. So if we check the type of prop run actions with options, we see first it takes the check options type that we have seen before when we did the emulator trace based testing. Then it takes this instance spec, so the contract instances we want to run. Then it takes something from model state to trace predicate, so this would allow us to insert additional tests. And finally, it produces a function from actions, which is basically just a list of actions, to property. Property is like a beefed up bool. You can think bool of that. It's a quick check thing. So it's a boolean that has some additional capabilities it's mostly for logging and debugging. So how do we use this here? So as options, we use the same as before, which allows us to specify the initial coin distributions. And what we do is we get each wallet 1,000 ADA and the wallet's NFT and 1,000 of both tokens A and B. Okay, as second argument, we provide these instance specs that we defined above, and we don't add any additional checks. So this is just pure true. True is just another word for return. It comes from applicative. If you check again, so we provide the first 3 arguments. So the result of this is now a function from action state to property. And provided QuickCheck can compute random actions, it will be able to test that. So this is now something QuickCheck can handle. So we can actually try this. And we can use sample to generate us sample action sequences. So, and again, we see this pattern that we saw with intlist before, that it starts simple and gets more and more complex. So the first one here would just have one action. It would just start the token sale for wallet 2. Second and third would even be the empty list, so no actions whatsoever. And then we see a more complex scenario. Start the token sale for wallet 2, start the token sale for wallet 1. Then wallet 2 tries to add 6 tokens to its own token sale. Then wallet 1 tries to set the price of wallet 2's token sale, and so on. And we see that we get quite complex scenarios. And what will this property be? I mean, what will be tested? Well, it will be tested, what I tried to explain in the diagram, that for all these randomly generated action sequences, the properties we specified in the model, so how the funds flow, correspond to what actually happens in the emulator. And if there is a discrepancy, then the test will fail. We can actually try this with QuickCheck prop TS, so which is called test here. So I can just call test, and we see tests are run, but we also see that it takes quite a while. So now it has run 18 tests, and it will run 100. Probably it's more interesting to implement a bug in the actual code and see whether these tests will find it. For example, set this transition. We insist that only the seller can change the price. But let's say we forgot this, so we don't post that condition. And if I now reload and call test, then QuickCheck indeed finds the bug, finds a counterexample. So let's see what that looks like. So after 13 tests and 2 shrinks, and this is the action sequence that led to the bug. So let's see. Wallet 2 starts the token sale. Then wallet 1 sets the price of this token sale that wallet 2 started to 12. So recall, I just removed the check in the state machine. So when we run this in the emulator, it will actually succeed and set the price to 12. But in the model, we specified that it won't have an effect if somebody else tries to set the price. So the model still believes that the price is 0, but in the actual code, in the emulator, the price is now 12. Now wallet 2 adds 11 tokens, and now wallet 2 buys 1 token from itself. And so according to the model, the price should still be 0, so this should be for free. The token should be for free. And therefore the model expects that the wallet loses the NFT, loses 10B because it gave 11, it added 11 to the contract, but then bought 1 back, so that's 10, and no change in ADA, because the price according to the model is still 0, because this action shouldn't have an effect according to the model. But in the emulator, it did now have an effect in the actual code, and we see that here we lost 12 Loveless. So this discrepancy in the flow of funds has been found, and QuickCheck reports the error, which is quite impressive, I think, that it comes up with this scenario which actually demonstrates the bug. Now, by default, this is all that the quick check tests do. So it only checks the flow of funds, whether that agrees at each point with what we specified in the model. But it is possible to add additional checks. And it is also possible to influence these action sequences. So right now they are just random actions, of course, checking the preconditions that we defined. But it's also possible to do some more unit test like scenarios where we specify certain flows of actions to steer the tests into certain directions. So that's called dynamic logic, and it's yet another monad. But I think that would go too far to talk about this now. And I should mention that, of course, this, even though it's very powerful, also has its limitations. So one thing is that, of course, it only tests the contracts that we provide. It doesn't test all possible off-chain code. So, of course, it's possible that with the provided off-chain code that we write, everything is fine, but some party could write their own off-chain code that allows them to steal funds from our contract. And obviously, this quick check model can't detect that because it has to use the contracts we give it in the perform method. And the second problem is concurrency. I mean, we carefully added this delay of one slot to each action to make sure that everything is nicely sequenced. So all the actions happen in sequence. But of course, in the real blockchain or also in the emulator, wallets can have concurrent submissions of transactions. And in principle, we could try to do that with this model as well, but then we somehow must, in the model, specify what should happen in this case. And that might really depend on in which order the transactions are processed and so on. So that might get very complicated. So there are limitations, but nevertheless, it's a powerful way to test Pluto's contracts. Finally, I should mention how all of this integrates with Tasty. And there's a function coming from the Tasty library called test property that takes a description, a string, and then a quick check property. So we can use our prop underscore ts here, and now we get a test tree that Tasty can understand. Actually, how this is now set up, if we look at the Cabal file, so we have the library with the three models we saw, the token sale and the quick check and the lens examples. And I provided an additional stanza in the Cabal file that's now not library and not executable, what we have seen before, but a test suite. And this means that the tests work by running executables, and if there's an exit code that's not zero, the test counts as failed. So the rest is quite similar to how we specify an executable in a Cabal file. So we provide a main. This is spec.hs. I haven't shown you that yet. And folder, other modules. So these are the two test models we have looked at. So this is the one with the emulator trace. This is the one we discussed just now. So let's finally look at this spec.hs. And this simply imports the two modules that contain the test and Tasty, and use this default main and set up a test tree. I can again provide some name and then just uses the tests we defined for the emulator trace and the test we now defined for the model. And all of this can then from the command line be run with Cabal test. If we do that, then after compiling, it will run all the tests. So in our case, two, the emulator trace test and the quick check test. For homework, I want you to modify the token sale contract to accept an additional transition called close that can be called by the seller and only by the seller to actually close the contract, close the UTXO, collect all the remaining tokens and Loveless in the contract and the NFT. And this time I don't provide an extra module for that, so you can either just modify this token sale module or copy it and create a new module with this separate logic. Of course, you will have to think about the datum type. So right now it was integer, but now we have this new state, this close state. So one option would be to use maybe integer instead, where just some integer, just price means the contract is still active and nothing means it has been closed. And if you feel ambitious, you can also modify the trace and the model in order to accommodate for this additional operation. So for the model, you could act new action close, and for the trace, for the emulator trace as well as a last step, provide the close action.